So I guess an explanation is in order here, right? Or maybe not. I don't know. Just in my last class of the day yesterday at 11 a.m., somehow it came up that I've got this Olaf from Frozen full body suit thingy. I'm like, should I wear that? And they said yes, so I'm like, I should just wear this for all class, right? Like, okay. Um, let me. I can barely see. All right. It's like Halloween. Without having to wear a jacket. Let's see. So as a warm up, wanted to look at f of x equals 3 times x to the fifth times 100 plus 10 ln of x plus x to the 10th. Find the derivative. Today we're going to talk about this thing called the partial derivative. It's a little strange at first, but I think once you get used to it, it's actually okay. Um, and the thing is, it's actually a great excuse to review derivatives, which is we've been doing so much antiderivative stuff. It'll be good to make sure that we get a chance to do some derivative review. So here's the warm up question again. You could very well, if you would like to, before taking the derivative, take that 3 and the 100, multiply them together and have a 300. You could do that, but I'm intentionally not going to because doing the warm up in this sort of peculiar way is going to help relate to an example that we look at a little bit later today. So to take the derivative, look, there's normally like three pieces here. I copied the 3 and I copied the 100. So if you want, you could have just stuck a 300 in front. This is this deal of you don't have to use a product rule. It's you got a constant times a function, so you could copy the constant and then differentiate the function. So this x to the fifth part was differentiated as 5x to the fourth here. But otherwise, the 3 and the 100 were copied. 10, in the same way, this constant 10 is copied. Whenever you have a constant times a function, you copy that constant. And then ln of x is differentiated 1 over x. And 10 to the x is a good reminder of the derivative rule for exponential functions. The derivative of 10 to the x is 10 to the x times ln of 10, right? Sometimes people forget about that factor. There's this times ln of whatever the base was. Just some comments, though. For the first term, right, this 3x to the 3 times x to the fifth times 100. This is a product. You could, in principle, technically use the product rule, but it's just not necessary here. When two out of the three pieces, so there's three pieces here, right? So when all but one piece is constant, you just copy the constants, right? So I copied the 3, copied the 100. Just the x to the fifth part was differentiated as 5x to the fourth. I want to actually be really careful today about this business about constant multiple rule because I think I say this phrase often enough, but sometimes people are like, what is, like sometimes the phrasing is people are like, what do you mean? So I want to really be careful about this by saying, even when we differentiate, like here's a smaller example. Even when we differentiate 10x to the fourth, often we just jump right away and we just often like multiply the 10 and the 4 directly, automatically, and just say that the derivative is 4dx to the third. That's fine. That's correct. There's nothing wrong with that. However, we are technically skipping a step. And when we skip a step, we might not even notice that the constant multiple rule is applying. I think it's actually helpful to clarify that that's what's happening. So I'm going to, it's not that I would expect people to write out as much as we're about to do, but I think knowing what steps are being skipped is helpful when you're doing a bigger problem where you want to talk about those details. So here, the constant multiple rule, just as a reminder, so derivative of 10x to the fourth, when you're differentiating, the thing you're differentiating has a constant and a function, and they're multiplied together, you get to copy the constant. So I'm really just trying to do one thing at a time here. Copy the constant 10, and then derivative of x to the fourth. So, and then to differentiate x to the fourth, that part is the power rule. So the 10 is copied, differentiating x to the fourth, giving you 4x to the third, that part, only that part really is the power rule. Sometimes we just go from here to here and say, oh, power rule. Like, it was really constant multiple rule applied, and then the constant multiple rule asks us to differentiate x to the fourth, and then that part is the power rule. So just to really clarify, one step at a time, going from here to here, that first equal sign right here, that's the constant multiple rule at play. And then differentiating from here to here, turning the derivative of x to the fourth into 4x to the third, that part really, that second equals here, that's really the power rule. I know it's a little picky, but like it's just good to right now have this reminder of like what's that constant multiple rule, because we're going to see kind of quite a bit of it today. Today, in fact, we have really one new idea, but it is today's really thing. It's mainly an excuse to review some derivative rules. Um, oh yeah, just before moving too far. Oh my goodness, this thing, like my glasses are fogging up. I don't know how long I can be Olaf right now, but all right. Um, yeah, I think we're gonna have to. Sorry, folks. We're gonna do that. Okay. Um, today's Thursday. Please finish the last online quiz. Office hours for the remainder of the semester are here. If these times don't work, just send me an email. We'll find another time to meet. But I gotta know, right? So send me an email and we can meet up. Final exam, you gotta choose your own 6 hour block of time in which to do it on either Tuesday, May 12th or Wednesday, May 13th. So today, what's the deal? I'm gonna move forward in slides here so I can see. Today we're gonna talk about functions with more than one input. Now, most of the time in algebra, we present this much simpler version just because like there's enough going on there usually, and our functions in algebra class almost exclusively and almost entirely throughout calculus tend to have one input variable and one output variable, right? Like just as a general setup, we say y equals f of x. As a specific example, f of x equals x squared plus 1. Right, so there's this input variable x, and when you plug in, so when the input is 5, the output is 26, right? 5 squared plus 1, you get 26 as an output. When the input is 10, you get 101 as the output. And just, I made a comment like this at the beginning of the semester, but I just want to clarify, this isn't two separate functions. That's not what's going on. There's one function here. There's just one function, f of x equals x squared plus 1. And what I'm doing in this right now is showing you two examples of using this function and talking about that input-output relationship. When you put in as an input 5, you get 26 as an output. When you put in 10 as an input, you get 101 as an output. And this is fine. Like there's a lot that is going on for functions which have one input or one input variable, but actually more realistic would be, yeah, it'd be more realistic to have functions that have two input variables and one output variable. So for instance, so like this y equals f of x, the way we phrase this here, well, okay, x and y will be well, x is normally an input variable like it was up here, and then the next letter y. I know that y over here we think of very often as the output variable, but x and then the next letter y will be the input variables, and so then the next letter z will be the output variable. So our new setup will be to have z equals f of xy. So as a tiny example of this, like f of x comma y equals 3x plus 4y. Okay, to find f of 5 comma 10, just be very systematic about it. The order in which these appear matters. So this 5, plug in 5 for every x, plug in 10 for every y. That's all we'll do here. So we'll have 3 times plug in 5 for the x, plus 4 times plug in 10 for the y. And I'd say just leave it like that. I just thought I'd demonstrate, though, that we get here in the end 55 when fully simplified. I have another example. Actually, I have several examples on the next slide. So, yeah, here's another. The top of the next slide has another example of a function with two input variables. So f of x comma y equals 3x plus y squared minus x to the fourth. So here's another function with two input variables. To demonstrate plugging into this, so I want to talk about f of 5 comma 6. So plug in a 5 every time you see an x in this. Plug in a 6 every time you see a y in this 3x plus y squared minus x to the fourth. We just plugged in. 3 times 5 plus, there's a y. The y we're replacing with a 6. 6 to the second. Copy the minus. There's an x. X we're replacing with 5. 5 to the fourth. I didn't bother simplifying this number this time, right? But that's going to be some number. Here's another example. I've got, now I've just named the function a new letter, called it g. So g of xy, and the output formula here is given by 10 times x plus x times y plus 5 times y squared times x. I could have put the x in front, but I just wrote it like this. And one of the other things is, let's be careful with 5 times y squared times x. I'm saying the times here, 5 times y squared times x. I could have just said 5y squared x, but I'm saying that times as sort of this reminder that this exponent 2 does not affect the 5, right? Order of operations still always applies. So here's a function with 2 input variables. And I have had discovered just the last hour a number of typos. So I'll fix these I'll fix these and re-upload slides. So yeah, you'll see. I'll just erase. There was an F there. It should be a G. Oops. So G of 3 comma 1. Plug in a 3 for every x. Plug in a 1 for every y, and you'd get 10 times 3 plus 3 times 1 plus 5 times 1 squared times 3. And I would just leave it like that, but just to illustrate a certain point in just a moment, I simplified that all the way down, got the number 48. I also want to talk about g of 1 comma 3. So now, to be real careful, notice all that really happened, at least in these two questions, is was it the see this g of 3 comma 1, this g of 1 comma 3. And here's where let's just be very careful, very methodical. Now the idea is that we should plug in a 1 for x and a 3 for the y. Earlier we had plugged in 3, like in the one that we just only finished up, we plugged in 3 for x and 1 for y. Now we're switching it up, plugging in 1 for x and 3 for y. So you get this, and it fully simplifies down to 58. And the whole point here, that's the only reason I wanted to simplify this all the way down to a 48, is these are different, right? So just be careful about g of 3 comma 1 versus g of 1 comma 3. But if you just plug in order, like look at the order that the variables appear here to help sort things out, then everything will go just fine. So one more example. This is actually an example of a function with 3 input variables. Okay, so I've got a function called h. The input variables are x, y, z, and the output formula is 2 times x plus 3 times y plus x times z plus 1. Here's a function with 3 input variables. And, well, let's find h of 10 comma 9 comma 8. So look, again, there's a need to follow an order. So we're going to plug in 10 for every x. We're going to plug in 9 for every y, plug in 8 for every z into this right there, right? So we should end up with 2 times 10 plus 3 times 9 plus 10 times 8 plus 1. Just plugging in replacing every x with a 10, every y with a 9, every z with an 8, whatever that looks like. And I didn't bother simplifying further for this one. Okay, so I hope so far conceptually we have something that's like not so bad so far, right? There will be some little sticky part to this in just a moment. What I should say is in all of what we're doing on this slide, it feels like algebra. Well, because it is. I mean, it's not algebra that's typically been done, but just plugging in numbers into a function, that's very algebra. That's an algebra thought. So where's the calculus? It's coming up, but before doing that, to lead up to it, I think I should talk about what's going on here. And just even a slide ago, I said that it'd be more realistic to have a function that has 2 input variables instead of 1 input variable. What do you mean more realistic? Because maybe sometimes functions themselves at all don't feel realistic. So let's make this very realistic for a moment. So often in algebra and in calculus, we just stick with y equals f of x because it keeps calculations easier. But really, when you have a function with 2 input variables, it's more like reality. What I mean, like in real life, you'd have a quantity called z, and it doesn't usually depend on just even 2 quantities. Like, so even 2, it's like I say, it's better, it's more realistic, but it's still not even realistic. Like most of the time, you'd have not just 2 quantities, but like z would rely on many quantities. So like here's a in a sense a small example. Like let's just say you have a small restaurant, right? Like just a tiny little restaurant. In if z represented the profit of a restaurant, then z would depend on many quantities. And let me clarify what I mean by quantities. I mean anything that you would attach a number to, right? Like so like I just made a small list. I've never run a restaurant or worked in one, so I can't even like really speak to these things. But like you can imagine that the profit of a little restaurant, like not a chain or something, like is going to depend on how many employees are hired per year? Maybe like you have this small restaurant, and every year, due to people graduating and moving on, they have to hire new people every year, and so like they lose two people to graduations, and then they have to replace those two people. So maybe you have this small enough uh, business, a tiny restaurant where they hire two people per year. Just as an example, um, the pay rate of the cooks, right? Like, what's the hourly rate that cooks get, or that wait staff get, or the cost of lettuce, right? This changes during the season, right? Like, how much a particular produce item is, if that's a thing that this restaurant uses a lot, that the cost of lettuce going up or down, that's going to have an effect on the profit of the restaurant. How many customers visit in a typical evening? Like, how many freebies are given out? All of these. I mean, there's so many other things. I just wanted to think of a couple things that would affect the profit um, of a tiny restaurant. Like, all of these have numbers associated to them, right? And so many more things. Like, I probably missed a lot of big ones. Like a lot of things that are like probably more important in determining the profit of a restaurant. Well, so where's the calculus? What I want to do is I took this list here and I put this towards basically the top of the next slide. And what we're going to do right now is talk about a modified derivative. So let me clarify what I mean. So derivative, we know it's a rate of change, right? Because derivative computes a slope, and a slope is a rate or a rate of change. And the derivative detects change, and we're going to talk about slightly modifying what the derivative looks like today for these new kinds of functions. So the derivative is still going to detect change, but before just digging into example problems, because I think then it's too abstract. I'm going to talk about let's talk about an important question that a restaurant owner would want to ask. Like, how does a restaurant's profit change if all of these quantities here? Let's just stick to these 1, 2, 3, 4, 5, 6 quantities. Obviously, there's more than 6 quantities that determine the profit of a restaurant. But let's just stick to these 6 quantities and say a restaurant owner wants to know, how's the profit of the restaurant going to change if all of these? Now, we don't want to change all these numbers all at the same time. So to make things even possible to think about, let's keep all of these 6 quantities constant. So a fixed number, like number of employees hired per year, keep it being 2. The pay rate of the cooks, the pay rate is still the same as before, no raises for the moment. Cost of lettuce, let's just say, isn't changed. I mean, that's not all realistic, but one quantity is going to change. Which one? The one that's in red. So wait, nothing's in red. There we go. So let's just say, like, all of these things that are not highlighted in red, just run this thought experiment with me, are not changing. Those numbers remain exactly the same. It's unrealistic. It's unrealistic that the cost of a produce item is going to stay exactly the same for the whole year. But let's just go with it for a moment and just say that this restaurant is considering the option, the possibility of, instead of hiring 2 employees per year as they do, considering hiring more. Like considering hiring 3 employees per year instead of 2 employees per year. So that change in the number of employees by 1, how's that going to affect the profit of the company? I mean, that, or let's say, let's go back and say, okay, no, they're not even considering that. So the number of employees hired per year is still 2, but let's say that now, and the cost of lettuce is staying the same, and so, but like now the pay rate of the cooks, they're like, we should give those cooks a raise, right? And if they're going to do that, what changing that hourly rate that the cooks make, how's that going to change the profit of the company? You can imagine that if you pay certain employees more, that just paying those employees more is going to lower your profit, right? Like, because maybe it's the right thing to do, but it's going to lower your profit. You've got to think about, as a business owner, like, well, how much can I afford to do that? Or for example, same deal with the wait staff. The cost of lettuce, if that goes up, you can imagine that the profit goes down as well. How about this? This may be like, how many customers visit in a typical evening? Maybe it's a small enough restaurant where over the course of several hours in the evening, you get typically 50 people a night, right, on average, right? So if, let's just say that number goes up, like somebody decided like they're going to hold their birthday at a restaurant, and so instead of 50 people that night, there was 80 people, right? And so like that, more people visiting might actually have a positive impact on profit, because maybe the restaurant doesn't have to throw out as many things that they had to just have on stock just in case, right? Or what I mean, again, like I'm trying to think of some scenarios, but like you can see how if all other things equal, like so all of these other things kept the same, maybe changing the number of customers that visit in a night might increase the company's profit, for example, right? So that's what we're here to try to talk through, is like, let's talk about the situation where there's many quantities and most of them are not going to change. We're just going to talk about how if one quantity changes, then how does that affect the output? Again, here I think it's good to think about output being represented by profit. Some notation for this. So this thing's called a partial derivative. We're going to keep all variables constant except one variable. So f sub x, this is the notation that's meant to be a lot like f prime. This other notation, this kind of a curly shaped d and then f and then curly sort of d and then an x. This is a partial derivative notation. This is meant to look like this df over dx kind of notation that we've seen at least on occasion here and there. So both of these are notations. Both of these are notations for what happens to the output. How does your output change as the variable x changes but all the other variables remain constant? Same deal, f sub y means what happens to the output? How does the output change if just the variable y changes but all the other variables remain constant? This key phrase is all the other variables remain constant. And to start, we're going to only look at functions with 2 input variables. So let's dig into an example. So I've got this function f of x comma y equals 3x to the 5th times y to the 2nd times y times ln of x plus y to the x. And I'd like to find f sub x, meaning we're going to treat x like a variable and y like a constant. So to find f sub x, pretend y is a constant. That's the key idea here. What I mean is, like, let's just, like, I mean, okay, maybe this is a little silly, but like I think maybe it helps. As the question stated, maybe it's a little abstract. So I'm going to add on a bit of a story problem to this that I hope helps us think about what's going on. Like, let's just say, like, y is the cost of lettuce, right? And x is maybe like the number of employees being hired per year by this restaurant. And this over here is using only 2 variables, it helps predict what the profit is. And it's unrealistic that there's only 2 variables, but let's go with it right now, right? And so the idea is like, so y is constant, the cost of lettuce is not changing, but this restaurant is considering what would happen if we hired an additional employee, right? Instead of hiring 2 per year as we do, because we lose 2, like, let's hire an additional, and what's the effect of our profit? We want to know, how's our profit going to change as we consider hiring 1 new person. Can this formula predict this for us? And so we're going to pretend y is constant. And in fact, to drive this home, what I'm going to do is say, really, let's pretend y is a constant. Let's just pick a constant. Now this work that's here, it's not technically, should not be presented as part of an answer. I'm just including it because it helps us think. So like, it's almost like this stuff should be just like some scratch work off to the side. So pretend y is a constant. I just picked a constant. I just picked 10. I just picked a number, right? So in the warm-up that we did at the beginning, I remind you what we did was we took the derivative of 3 times x to the 5th times 100 plus 10 ln of x plus 10 to the x, and we got this, right? Because there were 2 constants here. We copied the constants 3 and 100 and then differentiated x to the 5th as 5x to the 4th using the constant multiple rule. 10 times ln of x, copied the 10 and then differentiated ln of x as 1 over x. 10 to the x, remember the exponential rule, we got 10 to the x times ln of 10. This, look at the reason I wanted that as a warm-up was because of this first partial derivative problem we're going to look at. So take a look at how if we had plugged in y as 10, we would have had this right here, right? So look, 3 times x to the 5th times, and then y squared. Well, if y is 10, then y squared is 100, right? So the thought process in which we differentiated this to get that, that's what I want to do here. So in fact, you might find it helpful to kind of shuffle your work before differentiating. I tend to not usually write this step all the time, but like since it's a first time, like okay, look up here. So 3 x to the fifth, y to the second. Well, look, if y is a constant, we're treating y like a constant, then y squared is a constant, right? Like in our example, again, this should not actually be included, but like if y was the constant 10, for example, then y squared would be the constant 100. So if y squared is constant, then 3 times y squared is also constant. So I just stuck all of this stuff that we're considering constant right here in parentheses in front. So if y is a constant, then 3 times y squared is also a constant. And then there's the variable stuff, and then if we differentiate, so treating, yeah, here was a typo, so I'll get this fixed when I re-upload. So this constant 3y squared in parentheses is just copied using the constant multiple property. X to the fifth is differentiated as 5x to the fourth. Next term, y, we're treating y like a constant, so copy the y. Just like over here, this 10 times ln of x, we copied the 10. The same reasoning, same thought process. There's a y here. If we're treating y like a constant, we just copy the y, differentiate ln of x, you get 1 over x. Y to the x, to differentiate y to the x, you get y to the x ln of y. Look, same reasoning as over here. So the 10 to the x, think of it just like that y to the x, right? So if 10 to the x, if its derivative is 10 to the x ln of 10, then the derivative of y to the x is y to the x ln of y. So the key thing here is to notice that everywhere that there was a 10, like even this hidden 10, that was really a 10 squared. Everywhere there was a 10 in the warm-up, there's a y in this question that we just did. I should pause. Where question came up? Where did you get the y squared? Yeah, good. You mean, I think you mean like right here in the thing I just circled, right? So yeah, okay, yeah. So the thing is, the original question has first term, like in the question, right? The question had the first term was 3 times x to the fifth times y squared. So that's in the short answer is that's where the y squared came from. But I'm going to say a little more to say. So it was built into the question. But what did I do with this? Is like I just shuffled the order because if we're pretending y is a constant, then y squared is a constant, and 3 is also a constant. So I just took the 3 and the y squared and just stuck them all together right here first. Does that sort of answer the question? That if we're treating y like a constant, we're pretending y is a constant. So then 3y squared, that entire bit there. So I've just erased. Sorry. That first of all, there is this typo. So let me put that back so that this is correct. But yeah, so yeah, where did it come from? It was hiding as part of the original question, maybe is the short answer to that. Okay. Thanks for the question. Well, all we're going to do today is see more and more examples, but let's just pause here and see if there's other questions. Olaf from Frozen probably shouldn't be drinking hot coffee, but here we go. Okay, so look, given a function with 2 input variables, to find f sub x, treat y like a constant. By the way, I'm using that language very carefully. Treat y like a constant. Sometimes what people do is they'll ignore y. This is a different thing altogether. If you just ignore y, I've seen people do it. Like it's like they'll take the question, and they'll just everywhere there's y, it's almost like they erased all the y's. That would be ignoring the y's. That's not what's going on here. We're not ignoring the y's. We're treating every y that we see like a constant. So let's just keep doing some examples. I think that'll help here, right? So in my next example, I've got I called it z, that's the output variable, but I'm focused more right here, that f of x comma y is 10x to the second minus 4x to the second y plus 12 times y plus 3 times x times y squared plus 6. And we're going to find f sub x. Also, we could have used the notation the dz over dx, but I'm going to just use this notation, f sub x here. Right? Now, if you like, because x, so this little x here is indicating that x is the variable. We're treating y like a constant, just like we did in the previous question. So if y is a constant, and you don't have to write a step like this. You may find it helpful, especially at first when dealing with this. If x is the variable and y is a constant, I like, let's just organize the constants first. So like 4 is a constant, y is a constant. Therefore, 4y is a constant. Um, Over here, well, look, if y is a constant, let me just pretend y is a again, just we could make up a number. Like just say that y is 2. I don't know. If y is the constant 2, then 12 times y would be the constant 24, right? 12 times 2. So this would be constant. So 12y in this example, I mean, again, I'm not actually using the number 24. I'm just saying, for the sake of argument, if we pretended just temporarily, just momentarily, that y was a constant, then 12 times y is a constant. And in fact, 12 times y plus 6, this whole thing is actually a constant, right? If x is a variable and y is a constant. And one more here, again, just because like maybe you prefer seeing when you do your derivative the constant first. 3y squared is all constant, so I just wrote that part first. X is the variable, and that's written here last. Now, I think at least organized like this with all these constants that are in parentheses. I guess 10 is a constant, but it's not in parentheses. But organized like this, maybe it's a little easier to think about the derivative. Your call. So 10x squared, using the constant multiple property together with the power rule, you have 20x to the first. Copy the minus sign. Copy this constant for y. Again, remember, we're thinking of y as a constant, so 4y is a constant. Copy the constant, differentiate x squared using the power rule, you get 2x to the first. 12y plus 6, that whole thing is considered a constant right now because y is a constant. So we get a derivative of 0. And then 3y squared times a function, right? So constant times function, copy the constant, copy the 3y squared, differentiate x, and you get 1. Let's try another one. Take the function, same function, and I actually, using the same, new questions, using the same function, I'd like to find f sub y. So we found f sub x. Just a moment ago, in the earlier question, we treated x like a variable and y like a constant. Now we're going to treat y like the variable, so x is going to be a constant. Everywhere you see an x, just pretend that x is like a 12 or x is a 30. Don't actually write 30, but just pretend you see a 30 everywhere you see an x. So f sub y. So I'm looking here, and 10x squared. Look, x is a constant. So this whole thing, 10x squared, is a constant. Derivative is 0. Copy the minus sign. I copied the 4x squared because that whole is constant times the function y. So the 4x squared, oh, come on. 4x squared is copied. And then the derivative of y is a 1. So I could have written in a times 1 here. Maybe I'll just do that right now. Same deal. 12y. Well, this is constant times the function. Remember, y is a variable, so this copy the 12 and then differentiate y, and the derivative of y is 1. So I could write in a times 1 there. Over here, 3x is the constant. If x is constant, 3x is constant. So copy the constant 3x because it's constant times a function. We just need to differentiate the function. The derivative of y squared is 2y. And then the derivative of the constant 6. Well, that's really constant, huh? 6 is a 6 is a constant just like x is a constant right now. And so we get a 0 for that derivative here. So these times 1s, maybe they could be written in, but they're not really required. And then as a follow-up, what I'd like to do is take the same function again, and I'd like to find f sub x of 1, 5. So we have f sub x of xy right here. This is like the partial derivative function. Now I'd like to take the partial derivative function and plug in 1 and 5. Right? So yeah, I just took this, the f sub x that we got, and then plugged in the 1 and 5. 1 for every x, 5 for every y. If you copy paste this here and replace every x with a 1 and every y with a 5, you get something that looks like this. Same deal to the other half of this to find f sub y of 1, 5. We had just computed, in the middle example here, we had computed f sub y of xy. So I copy pasted that down there, and I just replaced every x with a 1 and every y with a 5. So we have here, we have like up here the partial derivative functions, and then we have plugging in specific numbers into these partial derivative functions, we get numbers. In fact, like this last one, not that I'd be expecting anybody to simplify this all the way down. This is the number 38, and I wanted to simplify this to 38 to just make the following point. What's going on here is, let's say, in this formula up here, if let's say y is changing, starting at 5, if y starts at 5 and starts to change, if y grows from 5 to 6, while x remains constant, so x remains 1, then this 38, what is this about? It's saying that the output of this function changes by 38. So again, this is made up, but like if y represented, I don't know, like some company that has been hiring 5 people per year, but is thinking of hiring an additional, a 6th person. How's that going to change the company's, whatever Z represents? Profit, I don't know. Then $38. I mean, maybe this is not all that realistic because I'm trying to make it up on the spot, right? But like, that's what's happening here. So one of the quantities that the business has control over is remaining the same. Maybe it even doesn't have control over. A business does not have a control over the price of lettuce, but like it affects the profit, right? So like as almost all of the quantities are kept exactly the same, not changing, to all things equal, so we can compare, but one of the variables is changing values, is growing. You can use that. This partial derivative helps detect this rate of change. One other comment, like here is like in the past when we had a function of one variable, please remember that you had to find the derivative function first and then plug in the x value next. This is a reminder back to things like velocity. And in the same way, here when you have a function with two input variables, you should find your partial derivative function first, and then you plug in your inputs next. Right? That order matters because if you need to find like f prime of 5 and you plug in the 5 first, then you just end up with a constant. When you differentiate, you get 0. So you've got to wait to plug, just like earlier, you find the derivative function and then you plug in your x value. You plug in your input number. Same deal here. You take your function with 2 input variables, find the partial derivative first, and then plug in the input numbers that you're given. So I'd like to try this example. F of x comma y equals 3x to the 10th times y plus 2x to the 5th times y to the 7th plus 8xy to the 8th. I'd like to find f sub x of 12,9 and f sub y of 12,9. Again, just like the comment that was made, we need to first find partial derivative functions and then plug in 12 and 9. So in that order. So the partial derivative function, so f sub x, so treating y like a constant. Well, if y is a constant, then 3 times y is a constant. So I just copy the constant first. And then differentiate x to the 10th, and you have 10x to the 9th. Then if y is a constant, again, right now, x is the variable. We're treating y like a constant. So then 2y to the 7th, that entire thing is a constant. Copy the constant, or it's constant times function. So the function x to the 5th is differentiated as 5x to the 4th. Copy the constant 8y to the 8th here, and then differentiate x, and the derivative of x is this 1 that's right there. So then, now that we have the partial derivative function, we can plug in the 12 and 9. Right? That plug-in bit is the algebra thing of just every x is replaced with 12, every y is replaced with a 9. To find f sub y, we look back up to this, and now every time you see an x, think that x is a constant. If you need to pretend that x is a number, like just pretend x is an 8 or whatever, just pretend that x is a number. So how do we differentiate this? Okay, well, if x is a constant, then 3x to the 10th, that entire thing is a constant, so it's copied. The derivative of y is 1. If x is a constant, 2x to the 5th is a constant, so copy the constant, and then y to the 7th is differentiated using the power rule, 7y to the 6th. If x is a constant, 8x is a constant, so copy that. And then y to the 8th is the function part, and differentiate that using the power rule. You have 8y to the 7th. Then, to find f sub, now we have f sub y of xy, plug in the 12 and the 9 for every x and for every y, and then you get that number, which didn't bother simplifying. How are we doing? We're doing kind of okay overall. of another example. F of x comma y equals x times square root of 6x plus y. So find f sub x and find f sub y. By the way, this function with two input variables, I find at least when we're going to go take the derivative, it's kind of easier to think about that square root as a raised to the 1/2 power. So how do you find f sub x? Well, you have to treat y like it's a constant. Now, there's something kind of extra sticky about this problem type here. So just off to the side, like not that you should show this as work, but I think it'll help us think about what's going on by just saying, I really just picked a constant for y. Just off the, not that it's not part of the actual work, but to help us think about it, I picked 1000. I just picked a number for y, right? So I took this, wrote it over here. I just replaced every y. There was only one y, but I replaced that y with a 1000. I just picked a number. And just so I didn't get confused, and this was the original function up here is called f of x comma y, I just used a new letter, called it g. And so if you plug in a specific number for y, not that you should, right? I'm just like, this is often this scratch work that isn't presented. Then you end up with a function that only has one input variable, x. And the question becomes, how would we differentiate this? How would we find g prime? Based on how this looks. And I stare at this and say, hey, that's a product. And I wish that was a constant, because if it was, then I could just apply the constant multiple rule. But here, both pieces of the product have the variable, so we'd have to use the product rule, right? And if we have to use the product rule here on this, guess what? We have to use the product rule up there on that. That's the whole point here. So we'll use the product rule, and I did have another typo here that I'll fix when I repost. Applying the product rule, again, y is the constant, x is the variable. So first times derivative of the second. So copy x, that's the first. The derivative of the second, okay, well 6x plus y raised to the 1/2, oh, that derivative requires the chain rule, right? So 1/2 times the inside stuff, 6x plus y, raised to the, lower the power from 1/2 down to a negative 1/2. And then the chain rule part, where you have to differentiate the inside stuff. So this inside thingy of 6x plus y, we have to differentiate. Well, 6x differentiates to 6, and y differentiates to 0. Why does y differentiate to 0? Because, again, y is a constant. Okay, that's the first half of the product rule, and then after the plus sign, there's a second half. So, the second half of the product rule, the second part, I copied it. I just wrote it as a to the 1/2 power. So root 6x plus y, you could have written root 6x plus y here. And then times the derivative of the first part. And the derivative of x is 1. Make sure we're doing okay. And I had another typo in even just asking the question here. So now how do we find f sub y? I meant it to be worded like this. We talked about how to find f sub x. Now let's talk about finding f sub y. Well, pretend that x is a constant. What I mean is, like, let's just go back up here and let's just pick a constant, right? Like I picked x, I just picked 99. Again, this is not work to actually show. This is like stuff, just scratch work that shouldn't be presented. But I plugged in 99 for every, I just picked a number. I picked 99 for x. And I stare at this, and how would we find the derivative of this? Well, we don't have to use the product rule here. You could, but you don't have to, because while this is a product, the first part is a constant. So we could use the constant multiple rule. We would just copy the constant 90. If we had to differentiate this, I'd just copy the constant 99 and then differentiate this next part using the chain rule. So that's, in fact, then that's what we're going to do over here, right? So to find f sub y, I'll just rework it because I had a typo. So I'll just, why not just rewrite it? Yeah. So f sub y, how do we find this? Okay, remember, y is the variable, x is the constant. So we copy x because it is a constant. We're treating x like it is a constant. So we just copy the constant. And then we have to differentiate this part. Remember this, if you would like to, think of it as 6x plus y raised to the 1/2. Great, right? So now we need to differentiate this and put the result right here. So times. Well, to differentiate this, we need the chain rule. So 1/2. Come on, pen. There we go. Okay. 1/2. The inside stuff raised to the negative 1/2. So the inside stuff was 6x plus y. But the chain rule says we need to differentiate the inside stuff. So we need to differentiate 6x plus y and multiply by that result. So 6x, the derivative of 6x is 0 right now. Because again, I know it sounds so strange. It's the derivative of 6x is 0 because x is constant. So 6x is constant and the derivative is of 6x is 0. The derivative of y is the variable right now, and so that derivative is 1. Yeah, it's a little strange, but like you just do sort of the same thing you do back up with this this function h of y with one variable. Just apply that process as consistently as possible. However whatever derivative rules would have applied, having actually plugged in a number in sort of scratch work, you'd apply those same derivative rules when you actually do the partial derivative. Okay, so yeah, when finding f sub x, you need to treat y like a constant. Don't ignore y. Ignoring y altogether would be very different. If you just ignore y, try it. Just write down a problem and just erase all the y's and take a derivative, you'll get a different answer. Okay. Just to really try to clarify this whole, x is a constant versus y is a constant here. So to find f, here's a function. F of x comma y is x to the y power. So to find f sub x, you treat x like a variable, treat y like a constant. So if y is a constant, just again, I'm not going to write it this time. We sort of did that kind of thing over here, but pretend y is a constant. Let's just pick a constant. Let's just pick 6. I don't know. So x to the y is constant. X to the 6th. How would you differentiate x to the 6th? You'd use the power rule, right? So if you'd use the power rule to differentiate x to the 6th, that's what you need to do here when you differentiate x to the y. You treat y to find f sub x, you treat y like a constant. Use the power rule. So you have, bring that 6 in front, so bring that y in front. 6x to the 5th, the best way we could write this right now is y times x to the power y minus 1. But the other question here is, what about f sub y? To find f sub y, we need to treat y like the variable and treat x like a constant now. So if we treat x like a constant, go back here, look at x to the y. Treat x like a constant. X is the base. So to differentiate x to the y, treating the base as the constant, the x is a constant. Think about how you differentiate 3 to the y. Yeah, the derivative of 3 to the y is 3 to the y times ln of 3. So the derivative of x to the y is x to the y times ln of x, right? Using the exponential rule. So this I think is a good, I hope it's not too confusing of an example, but I think it's a good clarifying example of okay, we got to really treat the variable that we're not differentiating with respect to as a constant. So in this first one here, we got this because we treated y like a constant. And then we got this x to the y times ln of x because then we treated the base like it was the constant. How are we doing? I also think that honestly, on some level, sometimes these examples where there's only 2 input variables, sometimes is a little more confusing. So I have an example of a function with 3 input variables. And sometimes this helps, oddly enough, clarify what's going on. So I'd like to find f sub x, f sub y, and f sub z. Last example of the day, and then I have some quick comments, right? So to find f sub x, so x will be the variable. Treat y and z like they're both constants. So y and z are both constants now. So if y and z are both constants, then this entire underlined part, y to the 4th, z to the 6th, that's all constant. So we get to copy those, and I just put in some multiplication symbols for visual. But the only part that's differentiated is x squared, and you get 2x here. What about f sub y? To find f sub y, treat y like a variable. To find f sub y, treat y like a variable. Treat x and z like constants. So that means this x squared part is a constant. This z to the 6th part is a constant. I'll just copy those in place. I won't juggle the order. We should only differentiate y to the 4th. So you have another typo, but you'll have x squared copied because that's a constant, y to the fourth differentiated using the power rule as 4y to the third, and then z to the sixth is a constant because z is a constant right now. So z to the sixth is copied. One more over here, find f sub z. So what's the partial derivative with respect to the variable z? So treat z like a constant. Z is a, sorry, no, not. So treat z like the variable, and then x and y, these are to be treated as constants. And so if x and y are constants, this entire thing circled here, that x squared y to the fourth, that entire part is a constant. So your constant times a function. The function part is z to the sixth. So copy the constant. There it is, right? This constant is just copied. And then z to the sixth is differentiated. 6z to the fifth. I have another example in the slides. You can take a look if you'd like on your own at some point. I think I want to do a couple announcements since it's the last day. And yeah, so online quiz today, the last online quiz, please do that. Office hours are here again posted. If these times don't work, just send me an email. We'll find another time to meet. For the final exam, you choose a 6-hour block of time on Tuesday the 12th or Wednesday the 13th. I guess I keep skipping past this slide on other days. I think this is the last class day. We should just talk through it, right? That like in a 48-hour block of time, you choose a 6-hour block of time. I'd appreciate if you turn in a single file and in PDF format with all the questions that you will be answering in order. Like if the pages are shuffled, it does make it a little harder to spot things. I will post some practice materials and just like kind of information and expectation about the exams and all that kind of stuff in PDF format. It will be posted in Canvas, just haven't been able to get around to it yet. And then I would please suggest that you keep as current as possible with web work. There is no new web work assignment corresponding to today. It's too much burden. Today's topic is not it's not to be the main focus of the final, right? So just try not to stress about it too much. It'll be okay. You'll see from the practice materials posted. The last web work then was the one that I was asking folks to start yesterday, but due to the timings of things, both web work 43 and 44, their final due dates are Monday of next week, and since that's in final exam week, I thought this would be a good time to just make those extra credit. Why not? Then just some final words like thank you and I'm sorry, and I'm sorry just meaning like I think this just sucks for you all as a process of taking class. So yeah, I miss you a lot. Like I miss the actual interaction, don't get me wrong. And I think to me the last 6-7 weeks has let me realize some things. Like I do enjoy teaching math in front of a classroom, but like more important to me, I think I realized, and I've totally missed this part of it, is like every semester I have people who come up to me and say like, I'm gonna give up on your class or whatever, and we talk through it, and sometimes people need to, but it's those things. It's more than teaching math. It's those interactions where I get to like work with people and motivate them and help them out in difficult situations. Those are the things that I miss even more. And I recognize that this semester with all the changes, like there's a lot of things that I probably just don't even know of, but I've read about some of the things that you wrote when you filled out the mid-April survey and like challenging living situations. You might know of somebody who's sick. Finances are all over the place. Work schedules. There's a lot that's been going on, and I feel bad for you all. And this is maybe a strange, bizarre way to end a calculus class, but let me just say just a couple words here that like I think maybe some of the applications that this class focuses on, maybe they don't feel very relevant to you. They are the things that the faculty in CBA have asked us to cover, and I didn't even get to cover all of that, as you noticed in yesterday. But I'm just gonna, as morbid as this is, like let's keep this real for a moment and just let's bring up calculus in this way. So like taking a look at this disease, we look at the number of newly infected people per day. I wish this were a decreasing function, right? If I wish that f prime were negative. Not that I use this language all the time when I look at the news or whatever, but like let's put some calculus to this, right? Like I want the number of people infected daily to be going down, but I don't think that's actually. I have not been had time much to follow as much news as I want. But if there were no choice, if the number infected had to be increasing, then even here I'd want that to be concave down, right? I want the second derivative to be negative. Well, think about it. Do you want this or do you want that? If you had to have increasing, you want concave down, right? That's the shape you want. And this is, I think, what the media are talking about flattening the curve. Like they're just not using the terminology of concavity. But we actually, I mean, just trying to bring up how calculus really gives you the quantified language to talk about some of these things. And as on an entirely separate note, thinking about like minimizing the number of fatalities, that's a real optimization problem, and it's one that involves more than one variable. I actually do have, when I was living overseas, a friend I met who's an epidemiologist, and she uses math to to do this kind of thing. To minimize number of fatalities, what you do is you actually take a derivative, or rather a partial derivative, and you set equal to 0. And we're not going to do that, obviously, right? But there's a way to actually do these sorts of things. I guess I'll just end on this note to say, if you need anything, whether it's math related or for this class or not, just please reach out, even after the semester ends, and take care of yourselves. Thanks.